Okay, in the last video we were talking about how we can understand the sensitivity of a matrix with respect to a perturbation either in the B, the right-hand side vector, or in the A coefficients, or the coefficient matrix. So we started by looking at a linear system like AX equal B and asked if we assume a perturbation for the right-hand side, how much we should expect for the perturbation in X. Okay, so we started looking at this example. I have a matrix 2 by 2, and the matrix looks normal. I mean, nothing so special about it. There's no zero or anything on the diagonal. So we should expect, maybe if it's less than 1% error in B, I do not expect more than maybe 1% in the solution X. But let's verify that. So I'm going to solve for X first. I'm going to put breakpoint here and run it up to the breakpoint. So here's my solution, 1 and 0. Okay, so let's check if X is 1. So we're going to multiply A by X, so it's 4.1 times 1 plus 2.8 times 0. So this is going to be 4.1. Yes, that satisfies the first equation. Second one, 9.7 times 1 is basically 9.7, right? Fine, so the solution actually satisfies the equation. Now I'm going to change B to have less than 1% perturbation in the first element, and then resolve the equation. So I'm going to put breakpoint here and then just go up to there. Now this time I get an X like that, and if you compare the first X and the second X, actually these are very different. Like the second entry in the first solution was 0, but now in the second time around when I solve the system, I get very large number, like very large compared to 0. On top of it, my x1, or the first entry in X, used to be 1, but now it's actually less than the second entry. So the 1% or less than 1% perturbation in B led to more than 100% or so in the entries. Like the second one has more than 100% change. So how we can basically rationalize this? Is there any metric that we can say, yeah, okay, so the matrix is very sensitive to perturbation? You may think of, a determinant. Maybe you learned in high school that determinant is a good measure of saying if the matrix is singular or, ill conditioned or something like that. Now, if you go ahead and calculate the determinant of A, actually we have it here. The determinant of A is minus 0.1, so right? Let me just put the breakpoint here and rerun the code. So there you go. The determinant is not even 0. That means the matrix is not singular. It's well behaved. So the question is why small change in B leads to like this large variation in X. Okay, so determinant is not a good way of measuring the sensitivity of a matrix with respect to perturbation. And the tool for looking at the sensitivity of his linear system with respect to perturbation is called condition number. So let's look at what condition number is. So the condition number by definition is the maximum of, so it's capital M over little m, where capital M is the maximum of A times X divided by X for all X's. So basically you look for an X that maximizes this ratio, and the maximum of that ratio is called M. Similarly, you find for an X that minimizes this ratio, it's called little m. If you divide M, the capital M by little m, you get a number called condition number, or the kappa of A. Okay, so this kappa of A is also equal to the norm of A. So this double vertical lines means norm. Okay, so we can also find the norm of a matrix similar to the norm of a vector. So to avoid confusion, this double vertical lines means norm of a matrix. Okay, and so if you get norm of A and then times the norm of A inverse, that's equal to the condition number. Now, one quick note on the norm of a matrix. So norm of a matrix is very similar to a norm of a vector. So in this case, if I have a 2 by 2 matrix, the norm of it, because I didn't say norm 1 or 2 or infinity, by default, that's norm 2. And norm 2 by definition is sum of, or the square root of sum of squares. So you get this matrix A, and you raise every element of it to the second power, you sum them up, and you get the square root of it, exactly like this. So that's going to be the first element, 4.1 raised to the second power, 2.8 raised to the second power, 9.7 raised to the second power, and 6.6 raised to the second power. You add them up, and you get the square root of it. Well, actually right here, you get the square root of it, and you get this number. And that is exactly equal to, if I just type norm of A. You can see that these are identical. Okay? So anyways, So we discussed that the best way to do the sensitivity of a linear system with respect to perturbation in the B coefficient or A is to look at the condition number. Okay, so condition number needs to know what definition are we using, or what definition we are using for the norm, because the definition of the condition number involves with the norm. So for every norm we have a condition number, like condition number for norm 1, condition number for norm 2, condition number for norm infinity, and so forth, right? So in MATLAB we have to say what kind of norm are we using within the definition, or we want to use within the definition of condition number. So when I say condition or cond A comma 1 means calculate the condition number of A given that I'm using the norm 1 for all the norms in the definition of A. Okay? Alright, so let's go ahead and calculate the condition number of A in this case. Okay, so the condition number is 2000. Now, so what does that mean? Condition number has a minimum. So for any matrix you consider, the minimum condition number could be 1. You cannot go, or you cannot find anything with the condition number less than 1. As the condition number becomes bigger and bigger, the matrix becomes very sensitive to perturbation. So 2000 is much larger than 1. And I would say, by looking at the condition number of 2000, this matrix would be very sensitive to perturbation, and you see that. We just changed B by, less than 0.1% or less than 1%. And we saw that, a drastic change in the result. The reason is because the condition number is big. And if the condition number is big, the matrix is very unstable. It's very sensitive to the perturbation. Okay? All right. So with that, we covered the condition number. There's a little bit of theory in the lecture notes, basically to prove what is the bound on the perturbation in X given the perturbation in B. So I'm not going to go through the details. It's for you guys to go ahead and read it, but the gist of it is in order to do the sensitivity analysis, we look at the condition number, not the inverse or not the determinant. So these are not good measure. A case in point, now let's talk about the inverse. Let's talk about the determinant. A case in point could be a matrix with 0.1 along the diagonal. Okay, actually I have this example in the notes. Let's assume I have a matrix A with 0.1 along the diagonal and everything else is 0. Okay, and let's say you want to do the sensitivity analysis on such an A. Okay, if we go with the definition of A, or the determinant of A, as the metric for the sensitivity of A with respect to perturbation, then you calculate the determinant of A because A has a diagonal element only and it has 0.1 along the diagonal. If let's say the dimension of A is 100, if you have like 100 by 100 square matrix, then the determinant of A is going to be 0.1 raised to the 100 power. Okay, and if you do that, that is almost 0. So then what would we say? We would say this matrix is very singular because the determinant is 0 and if you do the sensitivity analysis on this, we should expect to be very sensitive to perturbation. Well, this is if we go by the definition of the determinant. That means the small determinant means more sensitive matrix. However, if you calculate the condition number for this matrix, 0.1 on the diagonal and everything else is 0, you find that the condition number is 1. Okay? Condition number is 1 means the matrix is very, very, very stable. As I said, the condition number has a lower bound. That means condition number is always bigger than 1. And if you find that condition number is 1, that means that that's the smallest condition number we get. And again, by definition, the more the condition number, the more unstable. So by looking at the condition number of 1, I would say this matrix is actually very stable. And now you see the analysis using the condition number and determinant is completely opposite. Like condition number says the matrix is very stable. Determinant analysis says the matrix is very unstable. So which one is correct? Well, another learning in this class is we always go by the definition of a condition number. So we never use determinant anymore to say if a matrix is ill-conditioned or singular or anything like that. We always rely on the condition number. It's a better definition. Okay, and I proved to you that by just looking at this specific example of the determinant of a diagonal matrix is 0.1 along the diagonal, we proved that the condition number is the better way to approach this problem. So, bottom line, never use inverse to solve a system. Always use \/ operator. Second, if you want to see if matrix is sensitive to perturbation in B or A, always look at the condition number, not the determinant of A. The larger condition number means the more unstable or the more sensitive to the perturbation. Okay, so this was the last discussion on linear system. So in the next video, we're going to look at more definition of matrices and another example on ill-conditioned linear system. Okay, so thank you so much for watching.